तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have discussed in our last discussion the velocity field characteristics of gallium arsenide, and we have shown that the entire reason for that sort of velocity field characteristics is due to the scattering of electrons from this valley to that valley. As it gains energy from the electric field, those electrons become hot, that is, they are no longer in thermal equilibrium with the silicon at that moment, and then get transferred onto that. Okay. So, they will come into equilibrium after that point, in the sense they have definitely higher energies. So, if you relax them, they will come back to this point. So, that is what we have seen, and also the other materials like indium phosphide, they have similar characteristics, because the energy band gap is 1.35 electron volts and this gap is 0.53. Okay. Now, this has some impact on the peak electric field and also the energy required to transfer the electrons from here to here. They are more than that of gallium arsenide. Gallium arsenide requires 0.36 electron volts. Now, this requires more, that means you must go to higher fields. Now, so we just go back to this diagram now. So, that illustrates everything. The peak electric field at which the complete transfer of electrons from the lower valley to the satellite valley, that is over by about 3 starts. The transfer of electrons really begins at 3 kV per centimeter and is complete, of course, by the time you reach that point. The negative differential mobility, if you want to call, you can call, because as increase the electric field, the velocity falls. So, the negative differential mobility region is this, that is due to the electrons getting transferred onto the upper valley. And in the case of indium phosphide, the transfer takes place at about 10.5 kilovolts per centimeter. Reason that delta E is 0.53 electron volts, and also since you subject it to higher energy, the peak velocity is more than that what you get in gallium arsenide. Okay. It is because it gets transferred much before that can go to that velocity. Here you need higher energy, so higher velocity. As a result, you have got 2.5 into 10 to the power 7 centimeter per second. That is the velocity. Okay. Now, one thing, a couple of things to note here. If you take a look at the silicon steady state velocity field characteristics, it never goes to the peak, because it remains in the lower valley, and this is, you give enough time for the electrons to settle down to that particular energy. Now, if you take gallium arsenide, it goes to the peak and the velocities in this range up to about 20 kV per centimeter are above that than that of saturation velocity of silicon. Saturation velocity of electrons in silicon is 10 to the power 7, whereas it is much more in this region. Okay, that is one thing to note. If you take indium phosphide, you can see it is from this point onwards, right up to about 30 or more than 30 kV per centimeter, the velocities are much higher. So, you can expect that indium phosphide devices can be a potential contender for high speed devices, but unfortunately the cost wise silicon is the cheapest among, next is gallium arsenide, next is indium phosphide. Understanding of technology, silicon is best understood, next best understood is gallium arsenide, the least understood is or more difficult process is indium phosphide. So, you will not go into this unless you really require that, because this serves quite a bit of purpose for high speed devices, and it makes it easy to make devices with heterojunctions etc., with gallium arsenide. Now, you can just see some of the other material, just for sake of completion I will just project these. I am not plotting the velocity field characteristics. Indium arsenide, if you take, it is a direct band gap material 0.36 electron volts and delta E is 1.28 electron volts. Okay. Now, the peak field is actually higher. Okay. In fact, if you remember, the mobility of electrons in indium arsenide is much higher than that of gallium arsenide. So, it gets raised to that field quite quickly and it gets transferred with much higher energy. This E t is actually the peak electric field. You can call it as E t or E peak. You go back to this curve, if you take, you can call this as E peak and this as V peak, peak velocity electric field at which you get peak velocity E peak, or you can call it as E t transfer, because that is the point at which the electrons begin to transfer to the upper valley. So, that is why we use it in a different ways. So, these are just information that I am providing. So, they also undergo this velocity overshoot or velocity peaking because of the transfer of electrons from the lower valley to upper valley. Indium antimonide much lower band gap, delta is 0.41, you have got much higher velocities coming up. Okay. And mobility is very high here. These are just information that I am providing you, but main material that we look forward to will be these two, gallium arsenide and indium phosphide, and between them also gallium arsenide. Now, couple of things. Supposing you take the energy versus momentum, let us take gallium arsenide. Once we discuss that, same thing holds good for indium phosphide also. Notice I am drawing it flat compared to this steeper, showing that the effective mass is higher here, 0.55 times m naught, 0.067 times m naught. So, when it is cold, that is when the electrons are not hot, that is when the field is small, electrons remain here. Okay. Now, what we say is the velocity field characteristics go through a peak, reason being transfer of electrons from here to here. Now, the plot that we are given there, okay, the plot that is put in this case, let me just keep it here, so that you can just okay. It goes through a thing like this, and that is almost 1 into 1.0 into 10 to the power of 7 centimeter per second. Why drive all this thing? Just let me put it straight away. 10 to the power of 7. This is 2.2 times 10 to the power of 7. Okay. This curve is derived or it is achieved at steady state. You apply electric field, give sufficient time, the electrons can transfer from here to here. Now, you have electrons which are suddenly subjected to this field. Now, that is the way one can understand it very easily. This concept is slightly involved, but it is not very difficult. All that you have to visualize is it takes time for electrons to get transferred from here to here. Okay. If I apply electric field, give enough time, okay, then it will get transferred to that. Now, suppose I subject it to this field, high field, right away. Okay. For example, if I put 10 kV per centimeter, you are down here, what would happen? the electron which is present here immediately is subjected to that high field, and it experiences the benefits of being here. What I imply is it experiences a smaller effective mass. Okay. So, it has got high mobility, but now the field that it experiences is very high. If I am here, it is a different issue, the field is low. Okay. But if I apply high field suddenly, launch the electron into a region where our high fields are present, then it will actually get accelerated to very high velocities. V is equal to mu n into E. Mu n is actually very high here. So, because mu n is high, and if electric field also is high, it gets accelerated quite quickly to high velocities. Okay. Before it knows, it has gone past this energy. See, if you give enough time, slowly you apply, it will get transferred into that. But now here itself it stays, it gets accelerated to high energy, okay, and there is a time gap between its acquiring high energy and the time between which it changes its mobility momentum from here to here. There is a momentum change. So, the entire difference you can view it as, to talk in more technical terms, the difference in the relaxation times for energy and momentum. It takes some time to acquire that energy. Once it acquires the energy, it goes and settles to the momentum required to go transfer from here to here. There is a momentum difference. After momentum is m into v, half m v squared is energy. So, it has to acquire that energy. Once it goes to that energy, you have got the momentum. So, if you do not like to understand it that way, you can say that there is a finite time which lapses before the electron gets transferred from this valley to that valley, and during that finite time it is moving at a much higher velocity. So, it goes into much higher velocity. So, notice here this curve 10 kV per centimeter applied. These curves are generated by simulation, a technique called as Monte Carlo simulation, where actually you observe the movement of each of those a group of electrons individually, statistical. Okay. Let us not bother about how it is done, but finally by that simulation they have generated this velocity field characteristics. The concept is, it because of this particular time lapsed, that is during the transient time, what is plotted here you can see is the velocity of electrons versus time. If you go back to the previous curve, this is velocity versus field, steady state field. So, if I am biasing at 10 kV per centimeter, I am here. During the transient condition, if I apply suddenly at 10 kV per centimeter, it will not go to this velocity. To go to this velocity, it has to go through this transient and go there. But because when it goes through this transient here, just notice here, in this portion when you see this, you are talking of low fields. Supposing when the electron is in the lower valley, it experiences 10 kV per centimeter, it will be right up there. So, it goes right up there before it goes into this portion. So, there is a time which is lapsed before it acquires, it goes from 0 velocity, drift velocity to that velocity. That is what is plotted there. Okay. Ultimately, what will be the velocity? If you see the velocity versus time for that, I will just explain one curve, other curves are same thing. Okay. So, 10 kV per centimeter to go through the peak, even right up to about 5 centimeter, 5 into 10 to the power 7. I have to keep going back and forth from these curves if I go back, but here 10 kV is somewhere here. Because the 10 kV is applied in this portion, it goes like that and then comes back to this portion in time, in the time frame. Okay. And the velocity is much larger, because V is equal to mu into E, E is much larger there. Okay. So, ultimately, if you wait sufficiently long time, what will be the velocity? that is 10 kV. If I take 10 kV per centimeter, ultimately it has come to this. In other words, what we are telling is the velocity of electron versus time will not follow just like this, it will go like that and come to that. And beyond that point, constant. So, that is this curve. If I apply 1 kV per centimeter, what would happen? 1 kV per centimeter, you are here. It does not move from here to here. Only when you apply 3 kV per centimeter and above, it has a chance to go from here to here. Okay? So, 1 kV per centimeter, it will remain in this portion and it will just go into that portion and settle down. There is a time left. There is a time gap by the time it acquires that energy. So, 1 kV per centimeter, if you take, you see that is a curve. So, what is the difference between the two curves? In a low field, there is a transient. It takes about 10 to the power minus 12 seconds to reach that velocity, okay, steady state velocity. Whereas, if I apply 10 kV per centimeter, it takes more time, of course, it goes through a velocity overshoot effect. So, you got a velocity overshoot effect. Okay. So, this particular effect, which is a transient effect, is called the velocity overshoot effect. So, then you can see now, if the electrons are launched into a channel where the fields are high, it will experience velocities which are in excess of saturation velocity. Ultimately, you may have saturation velocity, but during the time, this period, it goes through that. Okay. Now, let us see what will happen with distance. After all, with time, the electron gets accelerated with high velocities, and when it gets accelerated, it moves also. Okay. So, at the end of time, here if I move at the end of 1 into 10 to the power 1 picosecond, it would have moved through some distance. I can plot the same velocity versus time curve as velocity versus distance. In fact, what you have to do is velocity into time, you have to integrate. If I want to find out what is distance, up to this point integrate this curve, you will get the distance. So, if you plot velocity versus distance, I will have same curve, similar behavior. So, what we are telling is, you take a channel, launch the electrons into the channel with high fields, it experiences the transient effect, where the velocity goes through a peak overshoot effect during certain time. During that time, it has moved through distance. Now, let us take this 10 kV per centimeter. You can see that it goes through the peak, same peak value, but x axis is distance because you multiply time into the velocity by about 0.5 microns. It has almost reached. In fact, even right up to about 0.75 microns, the velocity is much more than 10 to the power 7 per centimeter. So, what are you telling now? What we are telling is, if I have a channel, okay, and if I launch I apply, I do not show the gate here right now. If I launch electrons here, okay, these electrons will move here. Let us say this is high field. These electrons will move here with velocity. What will be the velocity? Velocity versus distance. This is a channel. The gate is in between. Let us not worry about that right now, because after all the field comes between these two. You go through it like this. What we were concerned is, if the field is high, you end up with velocity saturation, that is steady state. But in the transient conditions, if I may have even 5 into 10 to the power 7 centimeter per second. That high, and this distance could be as much as 0.5 microns, 0.5, 0.7 microns. What are we telling? What we are telling is, suppose I reduce this distance here. Now, for this situation which I have plotted here, the average velocity will be, take the total thing divided by distance, average. Suppose I move it here. Now, you can see where the impact of this velocity overshoot effect is. Make the channel length shorter. This exactly works out against the belief of people that short channel effect devices, gallium arsenide will not give the benefit, because they were fearing that the velocity saturation Vs is almost same in silicon and gallium arsenide. So, when you go to short channel devices, you will not have any benefit, but now you can see in the initial region of 0.5, 0.6 microns, you will have velocities much higher than saturation velocity. Now, if I make the channel length shorter, that is, I put the contact instead of here, I put it here, which is about 0.6 microns or 0.7, even 0.7, let us say. I put it somewhere here. What happens? What is the average velocity? Right through the channel, the velocity is more than the velocity saturation. You end up with devices which can give Q j is equal to Q n into V, V average is above the 10 to the power 7, 2 to 3 times or 4 times the velocity of what you can get in saturation with silicon. This is the reason why you get transconductance with gallium arsenide, which is much higher than that of silicon, even when the device channel lengths are shorter. Okay. Now, only condition that you must have is, the only condition is where you get the gate control, that is the point at which the electrons must be injected. After all, you should be able to control the current. The real channel or the gate is the gate region. So, you must launch electrons right into the mouth of this gate, the source end of the gate with cold, so that from there it gets accelerated like that. Okay. So, what we are telling now is that clear enough? So, you get velocity overshoot effect over a distance 0.5, 0.6 microns easily. Okay. And you see, the more the field, more is the velocity here. Why? The electrons are in the lower valley, they experience higher field, V is equal to mu into E, mu is high, that is why you get that. In fact, let me finish this thing, because other 1 or 2 things between silicon and indium phosphide I can just quickly go through, because that is the same effect. Now, what we saw, the whole discussion came up because we are trying to find out 2 devices in our last discussion we compared. In one device, the n plus region comes right up to the gate. In another device, the n plus region is not there. We were concerned about that. Let us take a look at this. If this is understood, okay, if I put this region large, and if there are high fields present, which is very easy, 2 microns if you put, you can get high fields quite easily throughout. So, if I apply voltage here, I am putting the same curve. A situation where the drain quantity is put here, then you get a velocity like that. If the drain contact is far away, this is where it is launched. The electron goes through the transient within that 0.5 microns, rest of the 1.5 microns, suppose it is 2 microns, 2.1 micron, that is what we were talking of, I think last time, 2.1 micron if you have. Okay. When I apply voltage, this is only about 0.5 microns if I take, or 0.6, 0.7 microns. Okay. That is about that. Beyond that point, the velocity is saturation. That is like in silicon. So, a device with this long channel in the sense source drain contacts about 2.1 micron, undergoes that velocity overshoot effect initially, and rest of the portion, 3/4 of that portion, it is lower velocity. The average velocity is actually smaller compared to the situation where I put it here. Before it has reached velocity come down to steady state, this whole thing is the transient condition itself. So, if I put the contact at 0.5 microns, within that 0.5 micron, the velocity is high. So, you get actually you are operating the device in a region where these velocity transient effects are existing. It has not reached the steady state. Who cares whether it is in transient condition or steady state? All that you want is high velocity electrons. Okay? So, that is why in the two devices that we discussed, when the n plus contact was, let us just put that down now. In one device, I just put only the n layer. In one device, you had the n plus layer going all the way up to this point. Okay, and you put the contact here. Of course, here H etc. I am not showing that, and I put the gate here. So, if you recall, let me draw the diagram right there itself. I just plot it like this. So, I put a gate here. This was 0.5 micron. Remember yesterday's or previous lecture, this was 0.5 micron, and of course, etched and I am not showing that etching portion etc. Conceptually, this was 0.5 micron, this was 0.25 micron. Where are the electrons launched now to the channel? This is a channel. Now, notice the difference between the channel and the gate. Electrons are launched here, and the distance here is 0.5 micron, and this is 0.25 micron. What is this distance here? 0.5 minus 0.25, that is 0.25 divided by 2, 0.125. That means, the electrons here, velocity versus distance, if I see that is right up to this point, it is like that, and that one is like this, overshoot effect. So, the currents are higher, transconductance is higher. Now, in the other case, second case, this is semi-insulating. The second case, in fact, this was number 2 device yesterday, previous lecture. Number 1 was only this n plus is present here, and you have the source, and the n plus is present here, and you have the contact drain, okay? And this is the n layer, and the gate is present here. In fact, the gate is present exactly that point, same way. Sorry, the only difference is that n plus layer is removed from here. Now, what happens? This is 2.1 micron, okay? That is 2.1 micron, and this is 0.25 micron. So, 2.1 minus 0.25, that is about 1.85. 1.85 divided by 2. So, that is about close to 1 micron. So, if you plot the velocity versus distance here, let us plot it here. The velocity versus distance, if I plot from here, See here the electrons are launched here, it is as good as metal put here, n plus layer. Here the electrons enter the channel right here, it is cold here, it gets hotter and hotter as it gets moves inside. So, this is about 1 micron. So, before that everything is over, it has experienced, it has enjoyed its overshoot effect right at the beginning. By the time it has reached the gate, it is velocity saturation. So, over the most of the region under the gate, it is lower velocity. In fact, we saw it was about 1.1 into 10 to the power of 7 centimeter per second, whereas in this case the average velocity was close to 2 into 10 to the power of 7 centimeter per second, 1.9, that is what we saw. So, you can see this is a remarkable thing that we saw. Now, what do we conclude from here? What we conclude is, if I have to make a device with gallium arsenide, short channel device, you can't afford to make it like this, absolutely no use, because the GM is small comparable to silicon. You have to have a device like this. Best device that you can get would be this is merging with that. Self-aligned structures, let us take a look at that. There are several other curves which are there in my slide, but I will not show it right now. Since we are on this topic, let us get into this. Let us get back to other things afterwards. So, you need self-aligned structures. What is the meaning of self-aligned? You want it like this, best that you can get will be you have a n layer, okay, have a gate here, and you must have, and this may be n layer, you must have n plus layer like this. Directly into this edge of the gate, electrons are entering cold, and they right through the velocities are high velocity overshoot effect. Okay. And you can put your contact here, that does not matter. The contact, metal contact can vary. What is the problem with this? The problem is this is shorting with respect to that. It may not short, but it will give a very leaky device, nth metal and n plus region. One, the breakdown voltage between the metal and this n plus region will be very low, you can't afford to do that. So, people have been working on that. So, this is the targeted thing. That is, the n plus region must be there below this, you can't put the metal right into this point, that is the hopeless situation. So, all that you can think of is bring this layer as close as possible to this portion, that involves a lot of technology. Okay. One approach which people adopted is n plus layer, you want it here. Okay. All that you do not want is over here you should not have n plus. So, people were very clever. What they did was buried that n plus layer little bit below. I will put the diagram. So, one approach, self-aligned structures. We will go through self-aligned structures now. So, okay. Then I will write slightly below. Aligned devices, structures or MOSFETs. Okay. So, one of the approaches. So, what we told just now is not possible. What they did was same thing they put, take semi insulating gallium arsenide, okay, and then implant channel. So, you got a channel region there. This can be epitaxial layer, or people prefer that to be implanted, because with one device you can, one tool equipment like an implantation system, you can get everything. So, implant that, okay, and then put your metal here, gate. Now, I am putting it in slightly differently. You put an implantation here, with this as a mask. So, that metal layer acts as mask, you implant through that. Now, but use higher energy. So, use higher energy, those implanted high dose will come here, the peak of that if I plot. So, most of the implanted ions will come here. Okay. It is in contact with the channel here. You put it here, this is N plus, and it is self aligned very much. So, that is a very clever technique, where you implant a deeper, a buried N plus layer, buried in the sense it is below the surface, and then now put a contact here. Okay, it worked out all right, but the problem is this is in contact with that partially at least, the resistance between this portion R between the contact and the buried layer, there is a high resistance path, particularly if you are using a light dose here and heavy dose here, this region does not have many dopants. So, between the metal contact and the buried layer, there is high resistance path. So, that whatever you gain, you lose in terms of power dissipation, in terms of GM. GM is GM 0 divided by 1 plus GM 0 into R, that is effective, that goes off. So, now another technique that is used, we will go one by one before we go into those other whole lot of curves, because we can even skip those things. Second approach, so disadvantage, high series resistance. Coming from this portion, because implantation is deeper, you need N plus contact for reducing resistance, that is not present here, at least in this portion also, and a partial contact will be there into the channel region. So, second approach is even more clever. Okay. It is like this. Take a semi insulating gallium arsenide, implant onto that, and take a, get a N plus layer, N layer, you get a N layer. Now, what you should do is, the whole problem is if the N plus layer come into contact with that, realize a structure like this. A T gate, a gate which looks like a T. Okay. So, this is actually one metal, this is the gate metal, which is tungsten. Okay. Of course, even there also that sort of problem is there, in the sense after the implantation, here just let me come back to this, after the implantation of this, you must subject it to annealing. If I use this gate as the mask for implantation, the gate is in contact with the substrate, you must anneal it at 700, 800 degree centigrade to recover the damage. You can't afford to have a metal which is reactive with the gallium arsenide. So, you must put refractory metals here like tungsten as a metal gate. Okay. You would work out all right if that serves the purpose, but problem is here is series resistance. So, what we do is we go back to this type of structure, okay. And if I have a structure like this, how do you do that? What you do is, let us see, supposing you realize this type of structure, you can use this as the tungsten, this is another material, this is a mask. Okay. Let us take this structure that is realizable, and then what do you do? You implant. An implant, it is vertically going down. It is vertically going down, therefore, implantation takes place here. Because this is shadowing that. Underneath that, there will not be implantation. It is like putting that mask implant on board. This is self aligned. But where is the gate? Here. There is a gap between the gate and this drain contact. There is a gap between the gate and drain contact. You can make this as small as you like, 0.1 microns, 0.2 microns you can make by adjusting this. Okay. So, you can get close to self aligned structures here. The only problem here is, in fact, people have made not only devices, made some integrated circuits also using this type of structure. Problem is, this has got to be tungsten, W is tungsten, tungsten titanium alloy. Okay. And this quantity, this particular layer on the top, that can be a photoresist which does not get attacked during the etching of this one. So, how does it made? How is it made? Let us come back to the technology. I suppose this point is clear enough. If I can make a structure like this T type of structure, I can use that as a mask for implantation, ensure that N plus layer is in not contact with the gate. So, actual gate is here, and that is the gate length, that is the channel length. I can have this 0.5 microns or 0.25 micron, and I can have it 0.1 micron, 0.1 micron there, because that depends how much is this undercut is. So, there it is made, they make is semi insulating gallium arsenide, okay. Just going through how they do that. Then you have got N layer put or implanted, and then deposit tungsten all over. You can either deposit, okay, you can deposit all over, and then this is tungsten. On the top of that, put that second material. This can be photoresist, or you can use aluminum metal, because if you etch this quantity, that etchant should not attack, when you etch this one should not attack that. So, what you do is, after these two layers are put, deposited, you do lithography, photolithography, etch that portion. You have to draw one more diagram. I am just doing it easily by rubbing it off. So, you remove that by photolithography, etch it. Now, put it in a plasma etching system, which will not etch this, it will etch this. In fact, you can use CF4 oxygen, this will etch that, it will not attack this aluminum, okay, or photoresist. A photoresist which is resistant to the etching, this will remain. It can be, this is tungsten, and this can be photoresist aluminum or photoresist. It is easier to put photoresist because you can spin it. Now, subject it to reactive ion etching, which is not anisotropic, but isotropic in the sense it will etch vertically down, it can etch laterally also. So, you can it comes down here, and after that what happens? It will etch down, then etch laterally, because it is isotropic etchant. We are not using anisotropic etchant. Isotropic etchant will etch down and laterally also. So, when you do that, you have removed all this. Now, you have got that structure that you wanted. So, a T gate can be used like that. Okay. Problem, only problem that you have here is the use of tungsten refractory metal. You need that, because after that implantation, after you do this implantation now onto this portion N plus, you have to subject it to alloying, annealing, I am sorry, annealing at about 700 to 800 degree centigrade to recover the damages which have been produced, to push the dopant atoms into lattice site, all that you have to do. Okay. So, people just were looking into other methods of obtaining self-aligned structures. The whole thing, the key thing here is to realize a structure like this, but without metal, put the metal at the end aligned with respect to that. That is called, that technology I will discuss right now, because the entire focus now is to obtain self-aligned structures. We have discussed two types. One of them has problem of high series resistance, and both of them have the problem of using refractory metal. So, now the method that is quite popular, has been popular, is but bit more complicated technology, involved technology, is SAINT, self aligned implantation for N plus layer technology, SAINT. I do not know who invented that word, in the sense it has come nicely. So, it is the SAINT technology that we are going to discuss now. I will go through the PPT very quickly, so that you can just see one after another. Starting material is means, see, the whole thing is like this, get a structure like this which can be used for implantation. So, whole effort is to get a structure like this without metal, with photoresist. So, semi insulating gallium arsenide, spin photoresist on the top of that, do lithography, okay, remove the photoresist from there. So, all that is, I could put one diagram like this, but spin photoresist, open the window like this, use this as for implanting. You know, after all, you need to realize the channel region, semi insulating is not conducting, you must have N layer, 60 kilo keV silicon implantation, dose of 10 to the power 11 or 10 to the power 12. So, you get that layer there, that is the channel region which will be formed. Then an implanted layer, and then multi-layer resist is put, silicon nitride layer is deposited, because after all, after implantation you need to finally anneal, and when you anneal you must have a cap. Why do you need a cap? To cover this arsenic, to prevent the loss of arsenic. On the top of this is a tri-layer technique. Second layer is actually the photoresist, which is called chloropropyl methacrylate. Very easily you can dissolve it in acetone. Put another layer, which is silicon dioxide. Each one is used as a mask for next layer. Another photoresist layer there. So, you can have bottom photoresist, silicon dioxide, then photoresist, pattern that, open the window there. Now, you can see you are getting an equivalent of that T gate portion now, the center. H, top photoresist, okay. I have already shown you masked, developed, then etch this particular layer, silicon dioxide, using a plasma of CF2 and H2 plasma. You etch this. This is at, say, this particular top layer is acting as a mask for etching this one, is protecting that. Now, this is photoresist, this is photoresist. If without this layer, you can't do the etching. So, use the silicon dioxide as mask when you etch this one. That photoresist goes off when you put it in the etchant. Now, use this, go back to this, use this as a mask, keep on etching in the oxygen plasma, over etch it, you get the T structure, not in metal, silicon dioxide and photoresist. How much undercut is there? Precisely you can control by timing. This undercut, that undercut, here what is shown is metal, that will decide how much is the gap between the N plus layer and the gate. So, you can precisely control the undercut. In fact, I have shown you a graph here which shows etching time for the minutes versus undercut. I can put 10 minutes, you get about 0.2 microns undercut. This is undercut, which will decide the distance between the gate and the drain. Then, now go back to this curve is very helpful. This is the one through which you implant here with the metal, but whereas here in this particular case what you are doing is you implant using this mask. See the implantation coming through. So, wherever this is there, silicon dioxide is there, implantation does not take place, that is N plus. So, this is the channel which has a low dose of 10 to the power 11 or 10 to the power 12, this is 10 to the power 13 per centimeter square dose, very heavy dose at 200 keV, so that you can go deeper. Then, so I got now a channel region, if I can put the metal here, there is a gap this much, which corresponds to this undercut. That undercut can be precisely controlled by etching time. N plus implanted layer. Now, just notice what you do is deposit another layer of silicon dioxide. You can do that at low temperature, plasma deposition, 200 degree centigrade you can deposit PECVD silicon dioxide. That is how it comes. See, I deposit everywhere, it is conformal deposition, so it takes the shape of that. That is the oxide that you deposit. Now, the key thing here is that is second SiO2 layer. Key thing is I just put it in a solution which dissolves the photoresist. Okay? That is, this is the photoresist, this is SiO2. I put it in a solution which will dissolve that. What will happen? Whatever is above that will go, that is lift off. Okay. See, whatever was there over this region, so it is dissolved now in acetone. Whatever is above that, including that oxide, goes off. Now, you have got defined N plus region channel, and you have got an opening here which is smaller than that. Now, just that is all those number, the description. Okay. Make ohmic contact. You want to form the gate contact finally without subjecting it to any heat treatment. So, make the ohmic contact. You can see the source drain contact is put there. Okay. Now, what you want to do is put a metal contact here. So, all these are by lithography. Source drain contact, gold germanium. Notice here, by lithography you can precisely etch this portion because there is no oxide there. It is a very thin layer, just about 1000 angstroms or less. So, you can etch it, even a dip etching will do, but you can put whole layer in photoresist, remove that portion. Now, you can see, you can do lift off technique again for realizing metal semiconductor contact only here. In the sense, put photoresist everywhere, only in this portion. So, if I keep photoresist everywhere except this portion, I put it in acetone, the photoresist from everywhere with the metal lifted off, you will left with this. So, the key thing here is after this step realize metal in that portion. Now, you can see you got the MOSFET which is self aligned with the distance between this gate and this portion realized by that T that you have got. Okay. So, this is self aligned structure what you can get. With that, this is a very popular technique, Saint. Some slight modifications have come. The entire effort has been to achieve a gap between the gate and this N plus layer, controlled gate gap, which can be done with this self aligned implantation technique. Okay. So, I think the characteristics of this we will discuss next time.